You walk past a
For
construction
residents
site.
of the Fifth
A
Ward,
concrete mixer
the sound
spins
of
steadily,
progress is a
pouring out a
constant
thick gray
reminder
mixture.
of what's to
People
come.
casually call it pouring cement, but ask a structural engineer, and they'll correct you immediately. No, that's concrete.
Remember,
confusion
we refer
sounds
to this
minor.
as Portland cement
Yet it's
concrete,
like calling an
not
entire
just
cake
cement.
flour.
Understood. My mistake.
Cement is only one ingredient. It isn't the house, the columns, or the slab beneath your feet. It's simply the binder. Here's the mechanical twist. If you cast a solid block made entirely of pure cement, no sand, no gravel, you would end up with something extremely brittle. It might be hard, but hardness is not the same as durability. To
Completed
understand
building
why
standing
the
strong,
construction
revealing
industry
why
never
cement
goes
alone
all in
is not
with
the house.
100% cement, we need to peel apart concrete the way you'd analyze an engineered stone. Once you see it as a designed material system, everything begins to make sense.
Pure
Portland
cement is too brittle. It can't handle
the
the
most
tension.
common type
Doesn't it
today,
save money?
Not long term.
was invented in the
rebar
19th
is
century
essential for the
by
tensile
Joseph
strength.
Apston. He heated limestone and clay to around 1,450 degrees Celsius, creating clinker, which was then ground into a fine gray powder. When mixed with water, this powder undergoes hydration reactions, forming tightly bonded crystals. It sounds perfect on paper. The real issue lies in how it handles stress. Hardened cement has high compressive strength, meaning it can withstand heavy pressure from above. A good sample can reach 30-50 megapascals, comparable to placing several trucks on a small brick. Yet when subjected to tension or bending, it cracks quickly. The explanation sits at the microscopic level. Hydrated crystals grow in a random network. They create stiffness, but not enough bridging strength to stop cracks from spreading under tensile stress. A tiny crack, only a few micrometers wide, can race across the material like a fracture line in glass.
We compare
Sand
the
and gravel
compressive
exist
strength
to
against
solve
the curb
exactly
weight.
that weakness.
Notice how the
Fine and
specialized
coarse
alloys
aggregates
maintain
make up about
structural integrity far longer than
60-75%
the
of
standard
concrete's
chassis.
volume. They function as the skeleton, while cement fills the gaps and binds everything together. Remove the aggregates, and you remove the primary load-bearing frame. Cement would have to carry the entire structural burden alone, something it was never designed to do. This structure turns concrete into a form of engineered stone, not a rock shaped over millions of years, but one designed in a few hours of mixing and a few weeks of curing. In laboratories, researchers have cast samples made entirely of cement paste. The results are consistent. Once dried, the surface shrinks significantly, forming a network of fine cracks. This shrinkage comes from water participating in chemical reactions, while some of it evaporates. As the volume changes without aggregates to anchor the structure, internal stresses appear. You can imagine it like dried mud in a field, splitting into small plates. Aggregates act as crack stoppers. When a crack reaches a piece of gravel, it deflects or stops, slowing the overall failure process. Another detail often overlooked: aggregates are far cheaper than cement. Cement is the most energy-intensive component in concrete because it must be produced at extremely high temperatures. Replacing most of the volume with sand and stone improves mechanical performance while lowering costs and reducing CO2 emissions. Producing 1 ton of cement releases nearly 1 ton of CO2, roughly comparable to the emissions from a short domestic flight. Using 100% cement would therefore be mechanically weak, economically wasteful, and environmentally unreasonable. Seen from this perspective, concrete isn't cement with a few rocks thrown in. It's an optimized composite system. Aggregates carry most of the load. Cement bonds and transfers forces. Water activates the chemistry, and steel reinforcement handles tension when needed. From material structure, the story moves into proportions. In everyday construction, there's a common rule of thumb: 1 part cement, 2 parts sand, 3 parts gravel, 6 parts dry material in total. Many builders simply call it the rule of 6.
Now,
This
moving
ratio
from the
isn't
structure
arbitrary.
itself, we analyze
It
the
provides
mixture
enough
proportions.
aggregate
The
density for
breakdown
strength
clearly shows
while
the
keeping
precise
sufficient
percentages
cement
of the
to fill the
compound
voids.
elements.
Increase the cement too much, and the mixture shrinks more and becomes prone to cracking. Reduce it too far, and the stones won't bind tightly, lowering strength.
Okay,
Water
keep
is
an
the
eye on
most sensitive
consistency.
variable.
Add the water
Add too
slowly
much,
now.
and
How
the
much
mix
should I
becomes
add?
easy to
Just
pour,
enough
but
until it
dries
looks
into
right.
a porous,
Follow the rule of
weaker
6.
structure. Add too little, and hydration can't fully complete, preventing the concrete from reaching its intended strength. A water-to-cement ratio around 0.405 is often considered optimal. In other words, for every kilogram of cement, about 0.405 kilograms of water are needed. That small number can determine the lifespan of a structure for decades. Curing time matters just as much. Concrete doesn't dry in a single day. Hydration continues for weeks. Within the first 7 days, concrete may reach roughly 70% of its design strength. After 28 days, it approaches near maximum performance. Pour concrete and let it lose moisture too quickly under harsh sunlight, and the crystals won't fully develop. The result is a material that looks solid on the outside, but remains weak and porous inside. Looking at the entire process, concrete resembles a balanced recipe between chemistry, mechanics, and practical experience. Cement acts as the binder. Aggregates form the framework. Water triggers the reaction. Time completes the structure. So the original question no longer feels mysterious. No one builds houses from pure cement because cement isn't the house. It's merely the glue inside a carefully engineered material system. Next time you hear someone say, pouring cement, you might gently smile and say, that's concrete. And if curiosity keeps growing, there's another puzzle worth exploring. Why does 2,000-year-old Roman concrete still stand strong, while many modern structures have already begun to crack? That story still has many chapters left to tell.